Hello everyone, welcome to my presentation. My name is Jukka from Communication System Group in the Department of Electrical Engineering at Chalmers University of Technology in Sweden. It's my great honor to attend IEEE GLOBECOM 2022 and have this presentation. Today I've introduced our paper. The topic is Doppler Exploitation in Bistatic mmWave radio slam. Our co-authors are either from Chalmers University of Technology in Sweden or Temple University in Finland. And here I would like to thank Wymeersch AI Autonomous System and Software Program to support my work. And this is a picture from downtown Singapore. Suppose we have a base station with antennas at the top of this building, and there's a user equipment here, also with many antennas. This is a signal sent from base station to the user. The signals can also go over the complex propagation environment. As you can see, they can bounce by some small objects and generate multipaths. And the question we want to answer is following. Suppose one base station can send signals to the user. Can the user determine its position and synchronize with the base station and perhaps find additional information like its orientation? And can we also provide radar-like maps of the environment? So we want to solve this downlink mapping and positioning problem with 5 technologies. The picture on the right is the same as the one we had in the downtown Singapore, but more mathematical. Here we have a base station and we already know where it is. And here we have a vehicle with unknown position, unknown heading, and unknown color pairs. The signals sent from base station to the user could be the live site, as shown in this green line. And those signals can also be bounced in their environment. For example, the signals can be bounced by some surfaces, like a wall, and then reach the user. But since when the user moves, where the signal hits the wall also moves. So we parameterize the surface with so-called virtual angle, which is a reflection of the base station with respect to the surface it is affixed, like this one. So when the user is moving, even though the instant point is moving, but the virtual angle is static. So this is what the signal looks like at the user side. This is a typical millimeter wave observation model in the literature. This PK is the sent signal by the base station, and each channel is described by a channel gain, a response vector at the receiver side. It depends on the angles of arrival, and the response vector at the transmitter side, which is depends on the angles of departure and the delays and the Doppler. At the receiver side, you can have this kind of combiner, which basically makes the receiver listen to a certain direction. And given the observation variety and the knowledge about the send signal and the combiner, the channel estimator can recover the geometric information like those delays, angles of arrivals, angles of departure, and Doppler. Given those angles, delays, and Doppler, we then need to figure out what is the vehicle state and also map the environment. There are some challenges in the problem, like we need to map a prior unknown environment. And the measurement has unknown data association, which means we don't know which group of measurements is from which source. And the main focus of this paper is analyze how does the Doppler benefit this slam problem, as Doppler is usually ignored in most works. Then let's look into the measurement in more details. The channel parameters of each path depends on the underlying geometric among the base station, the user, and the landmarks, as shown in this figure. The delay is determined by the propagation distance and the clock pairs. The angles of arrival depends on the arrival direction of the signal and the orientation of the UE. The angle of departure depends on the direction of the signal and also the base station orientation. The Doppler can be calculated by projecting the UE velocity on the arrival direction of the signal. Therefore, Doppler is positive when the UE approaches the landmark, and it is negative when the UE moves away from the landmark. The Kramer-Rho bond is a common approach to predict the performance of the problem. The posterior Kramer-Rho bond is a lower bond that is similar to the CRB but takes a Bayesian perspective and also assume that there's a prior on the parameters. And it indicates that the mean square error of an estimator should always be larger than the inverse of the posterior information matrix. And it has this form. And the inequality indicates the mean square error of the estimator is larger than the inverse of the PIM in the positive semi-definite sense. And the PIM is a counterpart to the FIM for the PCRB and can be decomposed into two parts, and with the elements given by these two equations. So the first part is the standard FIM, which contains information obtained from the measurement. And the second part is the prior information matrix, which contains prior information. To compute the bounds, we firstly construct the complete states of the system, the transition function of the complete states, and the measurement function of the complete states given the ground truth data association. And we then can compute the pain by this equation, where this H and F are the Jacobians evaluated at the true state, and R and Q are the covariance matrices. And this J is the PIM from the last step. Then we inverse the PIM, and the required bounds can be easily computed by these equations. Then let's look at the contribution of the Doppler. From the equation in the last slides, we know that Doppler of the current measurement only contribute to the PIM part, as Doppler-related components are only involving the Jacobian H and the covariance R. By definition, we can decompose H check into this matrix where this A and B are the Jacobians of the measurement function evaluated at the true sensor states and the landmark states respectively. Then we can further decompose the Jacobian A and B into Doppler-related parts and the non-Doppler-related parts. And these are how non-Doppler-related parts are calculated. And as we assume the measurement covariance is a diagonal matrix, and the diagonal block related to the UE and each landmark can be derived by these two equations. And clearly, Doppler provides non-negative information to both UE state and the landmark state, as these two parts are non-zero. To gain further insight, we expand Doppler-related Jacobians as these two equations. And from these two equations, we can see that for the UE position, the information brought by the Doppler is alongside the direction of the velocity, when the velocity is orthogonal to the path's angles of arrival direction. That also means that when the velocity is parallel to the path's AOA direction, the Doppler of that path does not provide any direct feature information. A similar argument holds for the landmark state. For the UE heading, the direction contribution is from the projection of the perpendicular velocity vector on the direction of the angles of arrival of each path. Hence, if the velocity is parallel to the path's AOA direction, so that the direct feature information is zero. For the UE clock bears, there is no direct feature information contribution. However, the direct contribution to the other dimensions still benefit this dimension of the clock bears. Therefore, if the UE moves alongside the same or the positive direction of the angles of arrival, the corresponding group of measurements does not have any Doppler-related information. Moreover, a smaller covariance of Doppler results in larger additional Doppler-related information. This figure shows our simulation environment. This is a base station as a triangle here, and 4 different services with the virtual angles at these 4 blue stars, and the 4 scatter points as shows as the red stars. And the vehicle drives around the base station with a constant turn rate, and the transmitter and receiver are both implemented with an 8x8 antenna array. And more details about the setting can be found in our paper. And also we implement the EKPMB SLAM filter to solve this SLAM problem. Then we move into the numerical evaluation of the results. We use so-called Gauss-Bar distance to evaluate the mapping result, which is a distance that considers all the estimation error and misdetections and false alarms. We also evaluate the RMSE for the positioning performance. And we firstly analyze how different levels of sigma d affect the bounds. This figure shows how the bound change with the sigma d compared with the bounds without considering the Doppler. From the figure, we could see that involving Doppler as a dimension of the measurement improves the positioning and the mapping performance, as error bounds are always lower than the case where the Doppler measurement is ignored. And the effect is stronger when the Doppler measurements are more accurate. That means when the sigma d is smaller, the bounds are lower. We then implemented the EKPMB SLAM filter into 2 cases. When the first case is the Doppler is considered with sigma d is equals to 0.1 meters per second. And the second case is that the Doppler is not considered. And these are the results for the mapping performance, and we evaluate the performances for both virtual angles and the scatter points. This figure shows that the SLAM filter can map the environment for both cases, and the mapping accuracy improves with more measurements being received. As overall, all Gauss-Bar distance gradually decrease over time. And clearly, when Doppler is involved, the SLAM filter has better mapping performance as the solid lines are always lower than the dashed lines in both figures. And then let's look at the positioning performance. And this figure shows that considering Doppler results in better UE state estimates as lower RMCs can be required. And the reason of that considering Doppler as a dimension of measurement brings lower bounds. And in addition, it also helps the SLAM filter to solve the data association problem, which improves the average normalized weight for the correct data association from 0.67 to 0.86. Then here comes our conclusion. Firstly, the involvement of the Doppler helps the SLAM filter to acquire better mapping and positioning performance than the case without considering Doppler. Secondly, the better Doppler measurements are, the lower PCRB and the more accurate map and the UE state estimates will be. And then we have the conclusion that the involvement of Doppler helps the SLAM filter to solve the data association problem. And finally, the implementation of the EKPMV SLAM filter validates the theoretical benefits of involving Doppler. And our future work will include extending the UE model to model with the unknown speed and the inclusion of the high-dimensional channel estimation, as well as extending the problem to a slight problem. Thanks for your attention. Any questions?